All right, take out your notes and your calculators. Today we're going to look at the second way to find a rate law from a kinetics standpoint. On Friday you learned how to find a rate law from a mechanism. How do you do it? What do you do? Go to the mechanism and do what? Go to the slow step, yes. Rate is equal to K times what? The number, you look at the reactants in the slow step, and how many are slamming into each other is the order of the reactants. So if you've got two things slamming into one thing, it's second order with respect to the thing that there's two of, and first order with respect to the thing that there's one of, right? Okay, so a more common method actually of finding rate laws is through some experimental data. So today we're looking at method of initial rates. What I really want you to see, though, is what data you're given in this type of method, because students will sometimes work like robots and try to apply a totally different method to this. But looking at what you have, it has to be the method of initial rates. You've got some experiments, and you've got concentrations of the reactants, and you've got the rate that is coupled with each experiment. So all that happened is somebody went and changed the concentration of the reactants and measured the start rate, did it again, and then did it again. And so you ended up with 3 separate little experiments for the same particular mechanism or reaction. So the way we're going to do this first one is through what I call ugly algebra. You can do it mathematically, or you can do it by table inspection. We're going to do both, and you can choose which one you like better. This is the way you did it in pre-AP chemistry. For those of you who are new to this and took level chemistry, you didn't do rate law determination like this. So this is probably going to be the better way for you until you get used to it. Before you even start this, I want to write a skeleton of the rate law looking at the reactants. So rate is equal to K times, I'm going to take my 2 reactants, NO2 raised to some order, and F2 raised to some order. Our job in this process is to find not only the orders of the reactions, we also need to find what we call rate constant, this K, and the units with that. Okay? So the first thing you need to start with is pick 2 experiments where one of the concentrations is kept constant. What 2 experiments do you want to do? This is real life data, so it's going to be close to being kept constant, not exact. 1 and 3? Okay, we'll keep 1 and 3 constant. We'll look at 1 and 3 because here NO2 is kept constant, right? All right, so what I'm going to do is I'm going to, and just bear with me, do what I say right now, and then you'll see why in a second, but I'm going to take the one with the bigger rate and place it on top. I'm going to divide the 2 rate laws by each other. What does that mean? Well, I'm going to take experiment 3, put it on top because it has a larger rate, and I'm going to plug in everything I can into the skeleton of the rate law. I know rate, so rate of experiment 3 is 7.57 times 10 to the negative 3 equals, I don't know K. The concentration of NO2 in experiment 3 is 0.0480. I don't know the order, so I put X, and then the concentration of F2 in experiment 3 is 0.127, and I don't know the order there either, so I'm going to call it Y. Everyone see what I did there? So now I'm going to repeat it and do it for experiment 1. In experiment 1, I have 0.04, oops, sorry, that's not rate. Got to get to rate. Rate in experiment 1 is 1.90 times 10 to the negative 3. That's equal to K times 0.0482 to the X times 0.0318 to the Y. So now I'm going to use fancy math. I know K's cancel. This is why we keep one of them constant, because numerically something the same raised to the same power is a 1, right? So I can cancel those. So now I can look at the math, and this is where you need your calculators. I needed to divide 7.57 times 10 to the negative third by 1.90 times 10 to the negative third. What do I get? 3.98, which is really approximately what? 4. Okay? That is going to be equal to 0.0318 into 0.127 is about, I can see it, it's 4, right? 4 to the y. What does y equal? Y equals 1. So I'm going to go ahead and actually move it over to the right so I have room to do the next one. So I have 4 equals 4 to the y. Therefore, y is equal to 1. So the words that you should say, this is what order with respect to what? First order with respect to which reactant? F2. You got to keep those straight. The one that you canceled is not the one we're dealing with here. Okay. So now I'm going to go to the next one, and I'm going to pick 2 experiments where the other one is kept constant. What 2 do you want to pick this time? 1 and 2, because those guys are kept constant, right? All right. So which one has the larger rate? 1 does. So I'm going to put that one on top, and I'm going to do 1 over 2. Why am I doing that? Because you see how this divided by this gave us 4? It's easier to solve for an exponent if we're solving for a whole number instead of a fraction. You can still do it, but you might have to use natural logs and stuff, and so it just makes the math easier. So I'm going to plug in everything from experiment 1. 1.90 times 10 to the negative third equals k times 0.0482 to the x times 0.0318. I can put y here, or I know it's 1 now, right? Okay. Divided by experiment 2, 4.69 times 10 to the negative fourth equals k times 0.0120 to the x times 0.0315 to the first. Well, k's cancel. Okay. This has to cancel because I chose 2 experiments for that reason. So what do I get here? 4.69 times 10 to the negative fourth divided into 1.90 times 10 to the negative third. 4 is equal to, again, that looks like 4 to the x. Not very exciting. X also equals 1. X equals 1, so this is first order with respect to NO2. All right, we're going to determine the overall order of the reaction. Overall is just adding up the exponents. So what's our overall order? Second order overall. All right, write the specific rate law. Now this will dictate whether or not we put the k in there as a number or not a number. If this question comes before the question of determine k, you're allowed just to leave the k as a letter. Okay, so we had NO2 to the first and F2 to the first, and that's good enough. However, if this determined the rate constant was before, then you'd be expected, before part 3 here, you'd be expected to put the k in there, numerical k. But we need to solve for k. How do we solve for k? Any ideas? Which one? Any of them. No, don't say the slowest, because that has nothing to do with the slow step of the mechanism. Okay? These aren't mechanisms. These are overall reactions. Someone just observed the rate of an overall. So it doesn't matter which one you choose. The real way to do it is to find 3 different Ks for all the experiments, or 4 Ks, however many experiments there are, and average them. But we're okay with just take the first one and just plug the first one stuff in there. So I don't have it in front of me. What's the rate of experiment 1? 1.9 times 10 to the negative third. The units on that are molarity per second is equal to K times, what's NO2's experiment 1's value? 0.0482 molar raised to the first. And then the F2? 0.0318 raised to the molarity raised to the first. All right, so isolate K and just give me 3 sig figs on that K. 1.24. Now the units are crucial. let's just look at units how they'd be if we were isolating K by itself, okay? If we were isolating K, we'd take this and divide it by everything on the right. So molarity divided by seconds divided by molarity to the first is what? 1 over seconds. Divided again by molarity is 1 over second molarity. Okay? I'm going to show you a trick to this for finding units, which helps a lot, and it causes less stress because, again, this is one of those Ks you have to have unit fours, not four. Not equilibrium Ks. Kelvin is a K to some people, but the main one, we always have to have units on our kinetics K. The shortcut is as follows. 1 over the unit of time. In this case, it was seconds. Does anyone know where I got the units? Look back. Look at your table. It tells you your units, and it tells you the units on the rate. Okay? So, again, 1 over the unit of time times molarity raised to the overall order minus 1. What's our overall order? 2 minus 1 is 1. That's why there's a 1 there. If we were first order, what would the units be? 1 over seconds. If we were 0 order, what would it be? Molarity per second. Okay? All right, let's go to the next one. Now we're going to do one with table inspection. If you do table inspection, you're going to have to write a little statement explaining your work. Ugly algebra is nice in that your work is done. After you do all that stuff we did, that's enough on the AP. But if you do it by inspection, you kind of have to clarify what you did. This one is better for inspection because the numbers are much cleaner. So if we look at this, you're going to pick 2 experiments where something's held constant. What 2 do you want to do first? 1 and 2. So these are held constant. I know those would be the ones I'd cancel out. So as I went from this pressure to that pressure, what happened to the pressure? It doubled. What power do I raise that to? What happened here? It doubled as well, right? What power do I raise 2 to get the rate to be 2? 1. So this is it. This is first order with respect to H2. Here's the clarification statement you have to make. Because as pressure doubled, so did the rate. First order. I'll talk about pressure in a second. People are like, I thought it had to be molarity. We'll talk about that. We'll review that momentarily. So now let's pick 2 other experiments. What are those? 3 and 4. Whew, what happened there? Doubled. What power do we raise that to get, what was that? A quadruple. So what order is that? Second order. Second order with respect to NO, because as the pressure doubled, the rate quadrupled. Okay, so why are we using pressure here instead of molarity? Well, we've kind of already talked about this a couple times, but if you remember our ideal gas law, okay, if I was looking at pressure by itself and isolating it, I'd be dividing by V. I meant to divide by V. So if we divide each side by V, we get pressure is equal to N over V times RT. What's N over V? Moles per liter, so that's molarity. So because this is all done at a constant temperature, there's a proportionality between pressure and molarity. So we can use pressure in gaseous systems in lieu of molarity. Okay? So you treat it just the same way, even though it says pressure. The rate law will look a touch different, and I'll show you how you set that up next. So looking at this, determine the overall order. Third overall, good. Now, rate is equal to K times, instead of brackets, you do P of, what was first? NO raised to the, is it 2? Times P to the H2 raised to the 1. So we need to use P's instead of brackets, okay? So now if we're going to determine the rate constant, let's just look at the actual experiment 1. So rate, pick experiment 1. What's rate for experiment 1? 0.66, and it's millimeters of mercury, right? Per second is the unit on that. Is equal to K times 400 squared. And what's H2's partial pressure? 150 to the first. All right, so let's give me the numerical value for K. Just give me 2 sig figs. 3.8, 2.8 times 10 to the what? -8. Okay, let's talk about units. If I were to do it, let's do it the shortcut way first. Shortcut way is 1 over the unit of time. It's not molarity this time, it's millimeters of mercury, raised to 1 less than the overall order, squared. So that is our unit, 1 over seconds times millimeters of Hg squared. Does that make sense? If I have millimeters of Hg, divided it by this one here, that just gives me 1 over seconds, right? Then I divide by the square of them, I get 1 over seconds millimeter mercury squared. I like the shortcut a lot. I like it a lot. All right, let's go on to the next one. Now, if you're struggling with what we did so far, you need to practice and do your homework. This next one is as hard as they get. I don't even expect to see one this nightmarish on the AP, but just in case, I think it's always good to practice this kind of thing. So let's solve for this one, and I'll end up having to extend the page because there's going to be so much writing. First thing I want to do is, if I'm solving for a system like this that has 3 reactants, what do you think I have to find in 2 experiments? Where 2 of them are constant. I have to be able to cancel 2 out in order to solve for 1 of them. So what experiments would that be? 1 and 2. So I'm going to start with the one with the larger rate. I'm going to end up dividing 2 by 1. Okay? And so I'm going to get 1.19 times 10 to the negative second equal to K times 8.71 times 10 to the negative second to the X times 2.50 times 10 to the negative second to the Y times 4.00 times 10 to the negative third to the Z. And I'm going to divide all of that by experiment 1, 1.74. Now notice I'm using ugly algebra. You have to in this one. You cannot do this one by inspection. 1.05 times 10 to the negative second to the X times 2.50 times 10 to the negative second to the Y times 4.00 times 10 to the negative third to the Z. So what cancels? The K's and the Y's and the Z's. So I end up with, if I divide these 2 numbers out, I get 68.39 is equal to 8.29 to the X. Now, you're going to have to do logs here, and you end up taking the natural log of 6, or log, LOG, doesn't matter which one, 0.39 divided by the natural log of 8.29. When you get that, you end up getting an X equal to 1.997, which is pretty close to what? 2. So this is second order with respect to which one? Respect to A. Okay? So that was the easy part of it, because now we're going to run into a situation where we don't have two more kept the same. So, any clues? We know A, so we know what the exponent for that is, right? So we just want to keep now one of the other two constant, and I'm going to show you how we're going to use the A as an actual number. So just bear with me and do number 4 and look at 3 and 4. We're going to put 4 on top of 3 because it's got a bigger rate. But looking at this, you see how the B is kept constant. This is A, this is B, this is C. Our B is kept constant here. We know what A's exponent is, so now we can make that just a plain number, and then we're going to solve for the Z, or the order of C. So this is 7.58 times 10 to the negative third equals K times 4.20 times 10 to the negative second. But we know that this is a 2. I'm going to do it in green since we got it from the green. Times 2.10 times 10 to the negative second to the y times 4.20 times 10 to the negative second to the z, divided by 1.34 times 10 to the negative third is equal to k times 2.10 times 10 to the negative second. That's going to be squared again, because we just solved for that, times 2.10 times 10 to the negative second y times 2.10 times 10 to the negative second z. So the only thing that truly, we got our k canceling, but the only other thing that truly cancels is this y, right? So I'm going to have to treat all of these as numbers. When I do the division of the 7.58 times 10 to the negative third divided by this, I get 5.657. And that's equal to, now when I divide this squared by that squared, this is really 4.2 divided by 2.1 is 2, right? 2 squared is 4 times, this is 2 to the z. You see that? Right here, this is 2 to the z. So now I'm going to divide, and I get 1.41 equals, that sounds familiar to me. What does that sound familiar to? What's 1.41? Square root of 2. So we have a fractional coefficient here. Can we have a fractional coefficient? Yeah, we actually can, and it's not going to make sense to you until Unit 10. How does a fractional order make any sense? How does a half a molecule slam into something? That doesn't make any sense because you don't know about something called equilibrium substitution right now. So it's not actually a half a molecule. It's going to be a proportion to a previous step in the mechanism, and you're going to learn it later. So just accept fractional coefficients right now. You'll learn it when we get back from Christmas, okay? So this is half order with respect to which one? With respect to C. Okay, the fun continues. Now what are we going to do? We're going to now solve for our final. To do this one, I need to pick 2 experiments, but I don't want anything to cancel out now because I know A, I know C, and I need to find B, so I definitely don't want B canceling out. So what 2 can I pick where nothing cancels out? 1 and 4? Okay. I'm more inclined to go to 2 and 3 because they're closer together, so I can see them better. So I'm going to put 2 over 3. All right. And so I'm going to do 1.19 times 10 to the negative second equals K times 8.71 times 10 to the negative second. What do we do there? Squared times 2.50 times 10 to the negative second. We don't know y yet. Times 4.0 times 10 to the negative third to the half. Divided by 1.34 times 10 to the negative third equals K times 2.10 times 10 to the negative second squared times 2.10 times 10 to the negative second to the y times 2.10 times 10 to the negative second to the half. Okay, luckily I have all of this already figured out for us. I'm going to extend it a little more. So when I divide these two rates, I get 8.88 is equal to, k still cancel, and here I get 17.2, and there I get 1.19 to the y, and there I get 2 to the 1/2 power, which comes out to be 0.436. It's not exactly 2. I did it in my calculator, so. Okay. Now, I'm going to divide everything into, divide that into that, divide that into that, and I end up getting 1.18 is equal to 1 point. How nice does that work out? So what is y? 1. Okay, so let's just wrap this up really quickly. We don't even need to, let's not even solve for k. I know you know how to do that. Rate is equal to k times a to the, a what? A squared, b, b1, c, 1/2, and that's actually the next question on the next page. What's our overall order? 3.5 is our overall order. Rate is equal to k times a squared times b to the 1 times c to the 1/2. Okay. Without even determining k, we know the trick to find units. 1 over, what's the unit of time? Seconds times molarity raised to the 2.5. Those are the units on k. Are you going to see this on the AP? Yeah, probably not. But if you understood that and could repeat that, you are done with method of initial rates and never have to study it again, because that's as hard as they get. Okay.